So good evening once again, everybody. For this particular talk, tongue is very firmly in cheek. So the science I'm talking about, I think, is correct, but take it with a little bit of a pinch of salt. So we're basically asking the question, is Santa compatible with the laws of physics? In other words, does Santa actually break any laws of physics according to how we think Santa actually works in terms of delivering presents to children? So just to make sure everybody knows who Santa is this allegedly a rather portly, jolly fellow with a white beard and a penchant for wearing red suits. Now, although that obviously means that displays rather questionable fashion sense, that doesn't necessarily mean he can't exist. So the question is, what about the claims made regarding how Santa delivers presents to children on Christmas Eve? So it is alleged, because none of this is fact, of course, Santa allegedly visits all households on Christmas Eve to deliver presents to qualifying children. Now, what do we mean by qualifying? Well, if you like, it's defined by his naughty nice list, which might be 50-50, it might be skewed in one direction or the other. So can we reconcile this alleged feat of being able to deliver presents to all children on Christmas Eve, can we reconcile that with our understanding of science? And the way I'm looking at it is, can we use any of the science I've already described in previous talks to help us understand whether or not Santa exists? Now, you've had quite a few talks from me over the last 20 years or so. There's a few of them scattered on the screen there. We can use some of the science described in those talks to help us understand what's going on. But before I talk about Santa, let's just get the Christmas cracker joke out of the way first. Of all the elements, which is Santa's favorite? It is, of course, element 67, which is... Thank you for being polite and laughing at that particular point. And there it is down at the bottom of the periodic table, one of the rare earths, which is what I've been researching in my earlier days for many a year. And that was covered in a talk on the ABC of stellar evolution, which you had a long time ago. Best part of 20 years ago, I think that was. So let's remind ourselves of what it is we're trying to address. Allegedly, Santa visits households on Christmas Eve to deliver presents to children. And we're going to unpick that one bit at a time. We're going to start with, how many children is he actually delivering presents to? Well, how many children get Christmas presents? Let's assume the Earth's population is 8 billion. It just clocked through 8 billion just basically a few days ago. I believe that about 25% of the Earth's population are children. They don't necessarily believe in Santa, but Santa believes in them, so they're still children. 50% are eligible for Christmas presents on the assumption of the religion of the children or the religion of their parents. Now, of course, they don't have to be Christian because Santa would still give them a Christmas present even if they weren't Christian. So about 1 billion children get Christmas presents. That's assuming a particular ratio of naughty nice. Let's, for the sake of argument, assume that there were no naughty children in the world. A little bit of a stretch, perhaps, but let's assume they're all on the nice list. So Santa has to deliver presents to about 1 billion children. Okay, so he visits all these households, and he does it in one day. So how does he get there? Well, apparently he has flying reindeer, which sounds a bit dubious. So do we know that reindeer can't fly? Well, we know that insects fly, and we know that birds fly, and we know that pterosaurs fly, though you don't see them too often these days. And of course, some mammals do actually fly. What about reindeer? Well, if reindeer can fly, they choose not to do so for most of the time because no one's actually got a picture of a flying reindeer. So if they do fly, they don't do it very often. There is very little solid evidence for flying reindeer. But absence of evidence is not the same as evidence of absence. So just because we haven't got a picture of a flying reindeer doesn't mean they can't, okay? So scientifically, that cannot be disproved. So that is simply, the jury is out as far as that's concerned. But how fast would Santa have to go? Santa and his sleigh and his reindeer. Well, to visit 1 billion children in one night, and let's assume a night is about 36 hours, We can use the time zones of the Earth as the Earth spins, because of course midnight moves around the Earth. And so we've got effectively 24 hours plus the length of a night. It's not necessarily 36 hours, but that's close enough. Santa would travel at something like 2,000 kilometers per second. Not so far from the number that was quoted just a moment ago. In terms of the speed of light, that's tiny, absolutely tiny. 2,000 kilometers per second might sound fast, but it's less than 1% of the speed of light. No laws of physics are anywhere close to being in danger of being broken. And if you remember the Fiat Lux talk, I was talking about measuring the speed of light. We found the speed of light was about 300,000 kilometers per second when we measured the speed of light in chocolate in a microwave oven. So that is no problem at all. Now, no object can travel through space faster than light can travel through a vacuum. Remember that an expanding universe, this always catches people out, an expanding universe, the galaxies can separate from each other at speeds that are greater than the speed of light. So an expanding universe can expand faster than light, but nothing can move through space faster than light. So those are two quite different things, which is why I put that in brackets there. So if he moves that fast, wouldn't we end up with roast reindeer? Surely there's going to be a problem there. So just as we know that when meteors come into the Earth's atmosphere and when asteroids come into the Earth's atmosphere, the air in front of the meteor or the asteroid gets compressed, and that compression produces heat. We know compression produces heat. That's part of the ABC of stellar evolution, explaining how a star, when it's compressed, produces heat in the core, and that's what produces the nuclear fusion that ultimately powers the sun. So we know that if Santa was to go through the air very quickly in order to deliver all these presents, surely things would get very hot, even with an aerodynamic sleigh. Now, it's not quite how it's normally depicted on Christmas cards, but maybe it is rather more aerodynamic than people would think. But even so, you will still get that compression of air in front of the sleigh. So won't that mean the entire sleigh and Santa and the reindeer are going to be glowing really bright because they're going to be getting really hot? Wouldn't they be glowing white hot? We know that compression produces heat. We know that hot objects radiate light. And so Santa ought to be easily visible as a bright point in the sky. Or maybe it was. Okay, it's very difficult to talk about the fact that Santa Claus existed before Christ was born, but okay, maybe it's not the Star of Bethlehem when we see a bright light in the sky. Maybe it's all these people that claim to see UFOs in the sky. Maybe, again, that's because the sleigh is glowing white hot as it travels across the sky. But there's another way of thinking about it. What do we know that does not? What type of material do we know that does not absorb light or emit light or reflect light? There is a certain type of material that fits that criteria of no matter how hot it gets, it will not emit light. Dark matter, which you heard about a few years back. Dark matter will not absorb light and will not emit light. And therefore, if Santa's sleigh was made of dark matter rather than ordinary matter, then even if it got warm, it would not glow and it would not be visible. Not be visible in the optical part of the electromagnetic spectrum and would not emit any electromagnetic waves or absorb any electromagnetic waves. So it wouldn't appear on radar either, because radar would just go straight through it if it was made of dark matter. So it's all consistent. It all looks very nice. Okay, fine. Let's have a look at other feats. We've dealt with children and we've dealt with visits. What about households? He apparently visits various households and goes down chimneys, according to tradition. So how can Santa get down so many chimneys? He's a fairly portly gentleman, apparently, and if he wanted to visit a billion children in one night, he would have to squeeze down something like 3,000 chimneys each second, which a portly gentleman, perhaps 2 or 3 times the radius of myself, that doesn't seem feasible given the size of most chimneys. So is that impossible? Well, difficult, but not actually impossible. Because according to the weird world of the very, very small, quantum mechanics tells us that atoms are made of positively charged nuclei with negatively charged electrons going around them. So an atom is effectively a positive nucleus and negative electron. But if somehow you were to swap the electrons with a different particle called a muon, which is heavier, then the atoms would actually be smaller by a factor of about 200 or so. So in other words, if somehow you could change your atoms by swapping the electrons for muons, which are very similar to electrons, they're just heavier versions of electrons, if you like, according to the particle physicists, then all the atoms would be 200 times smaller. So instead of Santa being a large gentleman 1.7, 1.8 meters tall, would be just Jobbik. And would fit, well, probably smaller than that, would only be 1 or 2 centimeters in size. And so would fit down a chimney very, very easily. How you swap electrons with muons, well, I don't know. But it's okay, according to the laws of physics. If you did, he could fit down chimneys, no problem at all. Doesn't help if you don't have a chimney, though. So, of course, a lot of houses, apartments, etc., don't have chimneys. So how can Santa get from the outside of the house or apartment to the inside without going down the chimney? Quantum mechanics to the rescue again. Quantum mechanics says it is possible for an object to reappear on the other side of a wall spontaneously. Doesn't need a good reason to do it. It's just a relatively low probability, but it can happen. It's called tunneling, whereby you can go through an object that appears to be a solid object, and the laws according to Newtonian mechanics wouldn't allow you, in the sense that I can't just gently push my hand through this glass window or wall, because it's solid. But according to the rules of quantum mechanics, it is possible for objects to pass through each other and appear on the other side, even if they've never actually existed in the intervening space. It's a weird, which is why the title of the talk is Weird World, it is a weird property of quantum mechanics. So it is possible for Santa to get inside a room or a building or a house or an apartment without coming down the chimney and without having to burgle his way in by opening a window or opening a door. What else have we got? He does all this on Christmas Eve. He does this in 36 hours or so. All in one night. How can Santa make so many deliveries all in one night? Even if he was traveling at relativistic speeds between each delivery, and he's got 36 hours to do it, how can he do that? Well, one option, quantum mechanics again. It's really handy having quantum mechanics so weird because it can explain all sorts of things. We know that quantum mechanics tells us that subatomic particles can be in 2 places at one time. And they can do 2 things at the same time. For instance, an electron can spin clockwise and anti-clockwise at the same time. Imagine if the Earth could do that. So if that can happen with subatomic particles, why can't Santa do that as well? And if he can be in 2 places at once, why can't he be in 10,000 places at once? It's not disallowed by the rules according to quantum mechanics, which appear to be the rules that dictate how the universe works. If, for some reason or another, Santa could only be in one place at one time, then he would need some other way of making the deliveries, if you assume that that, for some reason, is not available to him. But there would have to be an alternative, and one alternative would be, if he has to go to various places, why is it impossible for Santa to simply distort space and time? We know that stars, indeed any massive object, can distort the space and time around that object. It most often is visible in the case of stars and very dense objects like black holes. But any massive object can distort space and time. And let's face it, Santa is quite a massive object because he's quite rotund. So maybe Santa is capable of manipulating space and time, in which case he doesn't have to physically travel the various distances to the various houses of the 1 billion or so children, because he can just distort space to bring them to him. Right, what else have we got? We've said visiting households on Christmas Eve to children, but he's got to deliver presents as well, so that's a bit tricky. How could Santa carry all of the presents required? It would require, let's assume that every child gets a present. So that means he's got to carry 1 billion presents in the sleigh. How can the sleigh possibly carry 1 billion presents, even if the presents are quite small? Well, warping space and time again. We know, for instance, that black holes are bigger on the inside than they are on the outside, just like the TARDIS. Okay, so why can't Santa pull off the same trick? Why is it impossible for the sleigh to be bigger on the inside than the outside? It is allowed by the laws of, if you like, the general theory of relativity, which distorts space according to massive objects. So as long as we have a massive object, whether that be Santa or something else, it is possible to distort space so the sleigh is big enough on the inside, even though it's only got a finite volume as seen from the outside. If black holes can do it, Santa's sleigh can do it. And if you're not happy with that, there is again an alternative that doesn't break any laws of physics. We think there are 3 dimensions of space: forward, backward, left, right, up, down. Those are the only 3 spatial dimensions that we are aware of, but some people think that there are more spatial dimensions, it's just that we can't see them. Some theorists think there are 10 spatial dimensions. So we know of 3, but there may be an awful lot more. Maybe Santa knows about these, in which case all you need to do is to take the presents and shove them into one of these other dimensions, which we apparently cannot see, so the presents would appear to disappear as far as we're concerned, but Santa just needs to go to where the child wants their present, and he will just pull them out of this other dimension, and they would simply pop into existence as seen by us, and then he could pass them over and put them under the tree. So that does not, again, break any laws of physics, because we simply do not know how many dimensions there are. We are only aware of the 3 that we can see. It doesn't mean there aren't another 3, another 60, another 10,000 dimensions. There is no reason why it has to be just 3. Okay, maybe he can do this. Maybe all of these things are possible. But wouldn't all of these things need a huge amount of energy if you're going to be moving fast and distorting space and time? So surely Santa and a sleigh and a billion presents moving at relativistic speeds would need an absolutely incredible amount of energy. True enough. So why not use a black hole? If you're going to use a black hole to make the sleigh bigger on the inside than the outside in order to get all the presents in, why not use the black hole as a power source? A black hole could, in principle, power a starship up to very high velocities, and black holes can power starships for decades. So a black hole to power the sleigh for one day is by no means out of the question. And there's an alternative. There's an alternative energy source that we're overlooking. We don't have to go and get a black hole and use that as the energy source. There is another energy source available to us, and it's the elephant in the room that everybody keeps forgetting. What happens to all the mince pies that are left out for Santa? So it's not necessarily everybody, but if some of the people that are expecting Santa to visit leave a mince pie, that's an awful lot of mince pies. What if Santa could convert the mass of a mince pie into energy? Because we know E equals mc squared. If you know the mass of a mince pie, you can work out the energy equivalent of a mince pie just by multiplying it by c squared. If Santa could somehow access that energy, I mean, nobody believes that he actually eats all those mince pies, surely. Yeah, okay, that's just silly. But if he could take the mass and convert it into energy, he's got an awful lot of energy to use to go flying around fast and distort space and time. So how much energy are we talking about? Well, one mince pie is about 50 grams, according to my calculation. So E equals mc squared, 50 grams is the mass, multiplied by c squared, we get a number like 5 times 10 to the 15 joules. Don't worry about how big that is just yet. Let's first multiply it by the fact that, let's assume a few percent of households leave mince pies. 90-something% don't. Maybe they just leave a carrot for the reindeer. But if a few percent of households leave a mince pie for Santa, then we can calculate, let's take it as, let's say, 20 million mince pies multiplied by that number there gives us that many joules of energy. 10 to the power 23 joules. If Santa can use the energy in a mince pie, then that's the amount of energy he has available to him for that particular night. Now, anybody but a scientist doesn't know what 10 to the 23 joules is, so let me convert that into something you might recognize. It's the same as the energy output of a nuclear power station running for 1 million years. That's how much energy is available, and he might have access to that in one night. not a gigawatt for 1,000,000 years, but all of that energy in just a few hours. So it's an enormous amount of energy, easily enough to send him close to the speed of light or distort space and time if he so wishes. How do you extract E equals mc squared from a mince pie? Well, I don't know how he does it, but just because I don't know how he does it doesn't mean he doesn't. Maybe there's more than one way of extracting E equals mc squared from a mince pie. The obvious way is to take a mince pie and collide it with an anti-mince pie in the Large Mince Pie Collider at CERN. That's one way of doing it, but there's a couple of problems with that. Is the fact that you can only do that at CERN, and where do you get the anti-mince pies from in the first place? Because people only leave you mince pies, not anti-mince pies. So we have to find a different way of getting the energy out of a mince pie. And there is an alternative way of doing it. It comes back to our old friend, what if you've got an extremely strong gravitational source, let's say a black hole, then all you need to do to get most of the energy out of an object, and it doesn't matter what the object is, whether it's a mince pie, whether it's a cloud of hydrogen, or whether it's a star, if you want to get the energy out of it, just drop it into a black hole. Basically, when matter tries to go into a black hole, it usually forms an accretion disk of all the matter that's trying to get into the black hole. That accretion disk gets very hot and radiates a huge amount of energy. Perhaps 10% or 20% or 30% of the matter that falls into a black hole actually gets radiated out in the accretion disk. Compare that to the amount of energy that comes out of a star when it burns hydrogen into helium. When it fuses hydrogen into helium, we only get less than 1% of that mass out as energy. E equals mc squared, only less than 1% comes out. Whereas by this process, we might get 10% or 20% or 30%, orders of magnitude more efficient than fusing elements in a star. So matter falling into a black hole, we know, can produce huge amounts of energy. For instance, a quasar, one of the most energetic objects in the universe, is basically matter falling into a black hole. I photographed one in 2020. I photographed a quasar that was on the other side of the observable universe using a camera but without a telescope, and the only reason that so much light was arriving at that distance was because it was so energetic in the first place. Matter falling into this supermassive black hole produced so much light it was possible to see it or image it with a camera even at a distance of 25 billion light years. So we know it gives us very efficient production of energy. How much energy do you get releasing mince pies into a black hole? Funnily enough, I can't find any numbers. I've done a search online, and I looked for all the research papers that talked about how much energy you get out of mince pies dropping them into a black hole. I could not find any. So there's a sort of a niche area if anybody wants to get into that area of research. So it can't be a very popular topic, presumably. How can Santa actually do all that? Although he's not breaking any laws of physics, if he distorts space and time, if he uses a black hole to make the sleigh bigger on the inside than the outside, if he manages to find some extra dimensions to hide the presents in. But how can he actually do all that? But remember, just because we don't know how doesn't mean he can't do it. All of these possibilities are allowed by the laws of physics. But as for how, well, one thing you have to bear in mind is, who says Santa has to be human? No one's actually seen him, have they? No? So maybe he is green with big ears. Nobody actually knows. So is Santa compatible with the laws of physics? How many laws of physics does Santa actually break? As far as I can see, the answer is none. So feel free to draw your own conclusions about the existence, or otherwise, of the portly, jolly fellow with a white beard and a penchant for wearing red suits. But of course, regardless of your conclusion, I hope you all have a very Merry Christmas. Thank you very much.